Hello listeners and viewers, welcome to Kaduna State Ministry of Education Radio and TV e-learning program designed for our SS3 and other students staying at home due to the coronavirus pandemic. The present administration under the able leadership of His Excellency, Malam Nasir Ahmed El-Rufai, is positioned as always to ensure that under his leadership, our students are not left behind in all areas of human endeavors, especially education. Kaduna State is the center of learning. Therefore, we want to ensure that our students excel in their forthcoming examinations and beyond. Students and other learners at home are given this opportunity in order to continue learning, as education is a continuous process. Different subjects will be taught in this program to assist students to perform excellently in the forthcoming Senior School Certificate examination being conducted by NECO and WAEC as soon as schools reopen. Teachers making presentations will always provide their names and phone numbers during each presentation, and they can be contacted for questions, further explanations, and/or clarifications. The following numbers and contacts can also be reached for expression of any concern or observation: 090-865-00545 or 080-383-62072. Our website is www.education.kdsg.gov.ng. Our email education@kdsg.gov.ng or education.kdsg@gmail.com. Our YouTube channel, Ministry of Education, Kaduna State. Our Twitter handle @Kaduna_MOE. Or our Facebook page, Ministry of Education, Kaduna State. Stay safe, stay at home, and learn well. Thank you, happy listening, and happy viewing.
Good day, learners at home. Once again, you are welcome to physics lesson on radio, television, e-learning program of Ministry of Education, Kaduna State. My name is Hassan Buki. Today we are going to continue on the topic electric field. So today we are considering electric field part 2. In the outline we have electric field intensity or electric field strength, then assignment. Electric field intensity or electric field strength represented using capital letter E. Now we said electric fields are represented by electric lines of force which show the direction of the fields and their intensity or strength. The greater the density of the lines, the greater the electric field intensity or strength. Now what it means here is that lines are used to represent electric fields, and these lines are called electric lines of force. These lines also give the direction of an electric field, which means that the direction of an electric field is indicated using these electric lines of force. And also, these electric lines of force determine or show the density of an electric field or the strength of an electric field. We say if the lines are so dense, then it shows that the electric field is greater. But if the density of the lines is less, it shows also that the electric field is less at that point. The electric field intensity or strength E at a point is defined as the force experienced by a unit positive test charge at that point. I take it again. Electric field intensity or strength is defined as the force experienced by a unit positive test charge, small q, at that point. Now we have a diagram here. We have a charge, positive q plus capital Q at this point. Then we have P, point P, a distance r, which means that this charge plus positive Q is at a distance small r from point P. Now we say consider the field round an isolated positive charge, capital Q, as shown above in the diagram. Suppose a small positive test charge Q is placed at point P. The field intensity E at point P, distance r from plus Q, is given by, that means what we are saying here, supposing a positive test charge small q is placed at point P, then the field, electric field intensity or strength at this point P, a distance r from plus Q, capital Q, is given by this equation. E, capital E is equals to capital F over small q, where capital E is our electric field intensity or electric field strength, our F is force, our small q is our positive, unit positive test charge. Now the unit of E, that is electric field intensity, is Newton per Coulomb. From the equation here, we know that F, force, is in Newton, charge is in Coulomb. So Newton per Coulomb, because we have force per Coulomb, so the unit of E, electric field intensity, will be is given as Newton per Coulomb. Now we call this one equation 1. We say E, that is electric field intensity, is a vector quantity. Why? Because it has both magnitude and direction. We said, and its direction is taken to be the direction of movement of a positive charge placed at that point. Now, for you to get to know the direction of an electric field intensity, if you placed a positive test charge at a particular point, the direction in which the test charge will move will indicate or show the direction of that electric field intensity. The force on the charge, that's the test charge small q, due to the charge capital Q, is given by F, capital F, is equals to big Q times small q over 4 pi epsilon naught times r squared, where our big F is the force, we have the product of the masses, we have capital Q, and then we have small q, which is the test charge, and then r is the distance between the two charges. And we have already seen this equation in our electric field part 1, which we have already studied. Now, if we substitute equation 2, we call this one equation 2. If we substitute this equation 2 into equation 1, we will have E to be equals to capital Q times small q over 4 pi epsilon naught r squared all over small q. Now, mathematically, if we do our division, we will have capital E to be equals to capital Q times small q over 4 pi epsilon naught r squared times 1 over small q. Now, this small q on the denominator, which is the denominator here, will cancel this small q on the numerator. And we will now have our electric field intensity, capital E, to be equals to Q, capital Q, over 4 pi epsilon naught r squared. And we call this equation 3. Now, equation 1 and equation 2, any of them can be used to calculate electric field intensity, depending on the informations given in a question. Examples. Number 1, it says, calculate the magnitude of the electric field intensity in a vacuum at a distance of 25 centimeters from a charge of 5 times 10 raised to power minus 3 coulomb, given that 1 over 4 pi epsilon naught, which is a constant, is equals to 9 times 10 raised to power 9 Newton meter squared per coulomb squared. Solution. From the information given, our data are sorted out. We have distance, small r, is equals to 25 centimeter. When converted to meter, because 25 centimeter is not the SI unit of distance, so we have to convert from centimeter to meter, which is the SI unit of distance, and that will give us 0.25 meter. Then charge Q, capital Q, is equals to 5 times 10 raised to the power of minus 3 coulomb. Then electric field intensity, capital A, is equals to unknown, question mark, and that is what we are looking for. Now, applying this applying this equation, that's equation 3 of our electric field intensity, we have capital E to be equals to Q over 4 pi epsilon naught r squared. Substituting in our values, we'll have E to be equals to 9 times 10 raised to the power of 9 times 5 times 10 raised to power minus 3 over 0.25 all squared. 0.25 squared. That will give us 45 times 10 raised to power 6 divided by 62.5 times 10 raised to power minus 3. And finally, our answer will be E, that is electric field intensity, is equals to 720 Newton per coulomb. Question 2. Two charges, small q1 is equals to plus 12 times 10 raised to power minus 9 coulomb, and q2, that's small q2, is equals to minus 12 times 10 raised to power minus 19 coulomb, are placed 2 meters apart. Calculate the electric fields due to these charges at points A and B as indicated in the diagram below. So here we have our diagram. We have point A and point B. We have our charges Q1 and Q2. Then we have the distance of Q1 from point A as 1 meter, because from the diagram we can see that from the distance from Q1 to Q2 is 2 meters, and A, Point A is in between them, and the distance from Q2 to A is 1 meter, which means automatically the distance of Q1 from A will also be 1 meter. So, first we are going to consider point A. Considering point A, E1, that means the electric field intensity, E1, due to the charge, small q1. The distance of q1 from point A is 1 meter. So, applying our equation, we will now have E1 to be equals to q1, small q1, all over 4 pi epsilon naught R1 squared. Substituting in our values, we will now have E1 to be equals to 9 times 10 raised to the power 9 times 12 times 10 raised to the power minus 9 over 1 squared. And that will give us, we know that 1 squared is 1. So E1 will be equals to 108 Newton per coulomb to the right away from point A. So this is point A, and we are considering point A. Now Q1, the electric field intensity E1 due to this charge Q1 at point A. If a positive test charge is placed at point A, Q1 is a positive charge plus 12, and then this is a positive test charge. Positive and positive, there will be repulsion. So the test charge at this point will move away to the right from point A. And that is why we said E1, the direction of E1 from our answer is to the right away from point A. Now we consider Q2. That's the second electric field intensity, E2, due to the charge small q2. And R2, the distance of Q2 from point A is 1 meter. So our formula, again, E2 will be equals to small q2 over 4 pi epsilon naught R2 squared. Substituting in our values, we will have E2 to be equals to 9 times 10 to power 9 times 12 times 10 raised to power minus 19 over 1 squared. And our answer will be E2 is equals to 108 Newton per coulomb. Also, the direction will be to the right away from point A. So let's go back to the diagram and see. Okay, so this is point A. This is our second charge Q2. If a positive test charge is placed at this point, okay, if a positive test charge is placed at this point, we will now have Q2, and Q2 is a negative charge. Okay, so what happens? Negative and positive, there will be attraction. This positive test charge will be attracted to Q2, and therefore the direction of movement of the positive test charge will be to the right also, again away from point A. So we have the resultant. Now we have two electric field intensity. We will now take the resultant. Therefore the resultant E will be equals to E2 plus E1. Why are we adding? We are adding because in our knowledge of addition of vectors in SS2, we learned that if we have vectors in the same direction, the resultant vector will be the summation of those other two vectors. So we've seen that all of them, their directions individually are to the right away from point A. So they are in the same direction, therefore that is why we need to add. That is why we have E to be equals to E1 plus E2. And the resultant E will be equals to 108 plus another 108, which is 216 Newton per coulomb to the right away from point A. That will be the direction of the electric field intensity as well. Now considering point B now again. So E1, due to the force Q1, the distance R1 also is equals to 1 meter. If we apply our equation of electric field intensity, we will now have E1 to be equals to Q1 over 4 pi epsilon naught R1 squared. Substituting in our values, we will have E1 to be equals to 9 times 10 raised to the power of 9 times 12 times 10 raised to the power of minus 9 divided by 1 squared. And our answer will be E1 is equals to 108 Newton per Coulomb to the left away from point B. So we have E2 due to Q2, and the distance of Q2, if you look at in the diagram, the distance of Q2 from point B is 3 minutes. So applying the equation, E2 is equals to Q2 over 4 pi epsilon naught R2 squared. We will have E2 to be equals to 9 times 10 raised to power 9 times 12 times 10 raised to the power of minus 9 divided by 3 squared. We will have E2 to be equals to 180 divided by 9. So E2 will be equals to 12 Newton per Coulomb to the right away from point B. Now we are considering point B. We said if we have Q1, which is a positive charge, if we place a positive test charge here, Q1 will repel it, which means that the test charge here will move to the left away from point B. Now considering Q2, which is a negative charge, if we place a positive test charge here, and this is a negative charge, there will be attraction. So the test charge here will be to the right away from point B. Now they are in opposite direction. Now because they have opposite direction, our resultant E will be equals to, it will now be what? Subtraction. So we have E1 minus E2. That means the bigger field intensity minus the smaller electric field intensity. So we have E to be equals to 108 minus 12, which is equals to 96. So the resultant electric field E is equals to 96 Newton per Coulomb to the left away from point B. Now we have two directions here. One is to the left, one to the right. So which one will be the direction of our resultant field? It will be the direction of the greater electric field intensity. And E1 is the greater electric field intensity. So the direction of the resultant will be in the direction of E1, which is to the left away from point B. With this, we have come to the end of the lesson for today. I will call on my second, Mr. Napoleon Kure, to come and give you an assignment to keep you busy at home. My name once again is Hassan Buki. Stay home, stay safe, and keep learning. See you in our next lesson. Thank you.
Hello, learners. You have just heard from my colleague who just concluded part 2 of electric field intensity. And with this, we come to the conclusion with an assignment to keep you busy at home. On the assignment number 1, you have in a uniform electric field, the magnitude of the force on a charge of 0.2 Coulomb is 4 Newton. Calculate the electric field intensity. In a uniform electric field, the magnitude of the force on a charge of 0.2 coulomb is 4 Newton. Calculate the electric field intensity. Question 2. Two similar but opposite charges, minus Q small letter and plus Q small letter, each of magnitude 5 times 10 to power minus 8 coulomb, are separated by a distance of 8.0 centimeter in a vacuum, as shown in the diagram below. And in the diagram, you have negative charge Q at one point and positive charge Q, all small letters, at the other point. Point P is 3 centimeters away from positive point charge Q and is 5 centimeters away from the negative charge. That's what we have on the diagram. You have to calculate the magnitude and direction of the resultant electric field intensity, capital E, at the point P. I repeat, two similar but opposite charges, minus Q and plus Q, each of magnitude 5 times 10 to power minus 8 coulomb, are separated by a distance of 8.0 centimeter in a vacuum, as shown in the diagram below. Point P is 3 centimeters from plus Q and 5 centimeters from minus Q. You have to calculate the magnitude and direction of the resultant electric field intensity, capital E, at the point P. Our references remain: 1. New School Physics by M.W. and Yakoha. 2. All-Inclusive Calculations in Physics by Solomon Dauda Yako. And 3. Senior Secondary School Physics by P. Onokeke and M.W. and Yakoha. I take the references again. Number 1, New School Physics by M.W. and Yakoha. 2. All-Inclusive Calculations in Physics by Solomon Dauda Yako. And 3. Senior Secondary School Physics by P. Onokeke and M.W. and Yakoha. With this, we have come to part 2, to the end of part 2 of our electric field intensity. In case of any question, any suggestion, or any contact inquiry, you can get in touch with us on this number, Hassan Buki, 080 6550 4346. Hassan Buki, 080 6550 4346, and Napoleon Kure, 080 3636 2105. Napoleon Kure, 080 3636 2105. You are reminded once again that coronavirus is real. That's the reason for this program, e-learning. And so you are advised to stay at home as you remain safe and keep learning as we have a good anticipation in your WAEC, NECO, and JAM exams. Wish you the best till we meet in our next lesson. Thank you. Once more, I remain Napoleon Kure. Thank you.